In this video cast, we'll look at an electrochemical cell quiz. An electrochemical cell is usually made of two differing metals, and the two metals are usually submerged in solutions and connected by a wire with some type of load in between. In this case, it's a light bulb. And connecting the two solutions is something called a salt bridge. Salt bridge is filled with cations and anions that replace the lost positive and negative ions from the solutions. Given the following information, answer these about the electrochemical cell above. Electrode A is made of lead, so this is Pb, and the solution is lead nitrate. So we've got some Pb positive ions in here, Pb plus 2 because it's lead 2 nitrate. Electrode B is made of manganese, Mn, and the solution that it's submerged in is manganese nitrate, manganese 2. So this is Mn posi 2. Question number 1 says, which is the most easily reduced metal? To determine this, we need to look at something called the standard reduction potentials. You have a sheet of standard reduction potentials on your yellow periodic table. And if we look on the yellow periodic table closely, you can notice that they're all listed from the most easily reduced, which is the highest electromotive force, or E with the little circle right here, to eventually 0, and then the lowest or least easily reduced. Notice they're always listed in ease of reduction. Here's lead 2, which is negative 0.13, and here's manganese, which is negative 1.18. So we'll write those down. Where lead's standard reduction potential, I'll just write it as SRP because stands for standard reduction potential, is negative 0.13. This is for Pb, which is electrode A. And manganese is negative 1.18. This is for manganese, which is electrode B. Now, a lot of confusion comes with this thing called standard reduction potential because there's about 6 different ways of saying the probability of being reduced, because that's in effect what this means. Reduction, if you remember from a while ago, is the gain of electrons. Oxidation is the opposite, and it is the loss of electrons. And so you can remember it as OIL, oxidation is loss, reduction is gain. Certain elements have the probability or possibility of being reduced easier than others. This is called its reduction possibility, or the fancy name is potential. Reduction potentials are measured in volts. And so sometimes you'll hear me and other people refer to as the reduction potential as the voltage or the volts of a particular substance. And if you look at these, you can see that it's listed right here as E circle volt. Now, why is reduction potential or voltage called E? Well, E comes from Electromotive Force. An electromotive force is the push that makes electrons move. And sometimes it's symbolized as EMF. Sometimes it's symbolized as a circle E like this because it's at standard conditions. Sometimes it's just simply an E like this with a circle, of course, if it means it's at standard conditions. And standard conditions for electromotive force or reduction potential or voltage is the same as it is for any other thermodynamic process, which is 25 degrees Celsius or 298 Kelvin, and 1 molar solution, and 1 atmospheric pressure. So anyway, getting back to these standard reduction potentials that we look at over here, the bigger the number, the more positive the number, the more easily it is reduced. So and it asks here, which is the most easily reduced metal? It's the most positive one. And in this case, it would be Pb because it's more positive than the manganese. Second question says, what is the balanced equation showing the spontaneous reaction that occurs? So if we know that lead is the most easily reduced, lead is going to go from lead plus 2, and it's going to gain some electrons, and it's going to go to lead 0 because it's gaining electrons, and therefore it's going down in charge. The manganese then, conversely, is going to have to go from manganese 0 charge to manganese plus 2 because it's losing electrons. And oxidation and reduction always occur in pairs. And so lead has electrons that are gained, manganese has electrons that are lost. And this is the balanced equation because you can see the charge is balanced on both sides, and we have the same number of leads and manganeses on both sides. Question number 3 says, what is the maximum EMF? There it is again, electromotive force. The cell can produce if everything exists at standard conditions. Now, to determine the EMF of a cell, what you need to do is take the standard reduction potential of something called the cathode, and from it subtract the standard EMF, or the standard voltage, of the anode. Now get over this right now, because remember there's about 6 different ways to say the same thing. E circle, EMF, electromotive force, reduction potential, volts. They all mean the same thing. They all mean, look at the number on the periodic table right here, because it tells you in a rating scale right here in terms of voltage how easily something is reduced. We have those numbers on here, and now we just need to define 2 more things, and that's these things called cathode and anode. They're really easy to remember. The way you can remember is if you know that the red cat and the ox. Reduction is the cathode, the anode is oxidation. Red cat, anox. So if you know what's oxidized and what's reduced, you know the cathode and the anode. The cathode is the thing that is reduced, and we saw here that lead went from plus 2 to 0, so it went down in charge. So that's our cathode, which had a standard reduction potential of negative 0.13. And we subtract from that the anode. The anode, remember, is anox, so it's the thing that's oxidized. And manganese went from 0 charge to positive 2. And its standard reduction potential right here is negative 1.18. So we take negative 0.13 minus a minus 1.18, and we end up with a voltage of 1.05 volts positive when you subtract 0.13 from a positive 1.8, because a minus times a minus, remember, gives you a plus. So this means that the potential difference between these 2 metals when they're connected in a wet cell like this is 1.05 volts, or let me say it like 5 different ways because it can be said 5 different ways. This is a potential difference of 1.5 volts. It has an electromotive force of 1.05 volts. It has a standard EMF of 1.05. Its E circle is 1.05. Its voltage is 1.05 volts. You can say it any one of those ways, and they all mean the same thing. They mean, what is the difference in being reduced between these 2 metals? Okay, question 4, what is the direction of the flow of electrons in the wire? Well, we see from the balanced chemical equation that manganese is losing electrons and becoming oxidized. So that means the electrons here are being lost, and they're being driven along this wire right here. Being driven along this wire right here, and they're flowing in this direction. The electrons are driven along this direction over here towards the lead. So we'd have to say that they flow from manganese to lead. From manganese to lead. What is the direction of the positive ion flow in the salt bridge? Now remember, the purpose of the salt bridge is that when electrons are gained somewhere, let's say an electron flows through this wire right here and it goes plop right here into the solution. Well, unless there's something to balance out this negative charge right here, no more electrons will flow in there. And so you've got to have something coming in there to replace this, to balance out this charge that's happening right here. And also, since this is losing electrons, you're going to have something come in here that takes the place of these electrons that are being lost. And so we have to say that since this is losing electrons, the negative ion flows into here, and the positive ion from the salt bridge flows into here. Think of it as a balancing act. Since we've got the negative electrons flowing in here, we need positives to balance it out coming out of the salt bridge. And since we've got electrons leaving here, leaving and going this direction, we're going to need electrons or some negatively charged thing to come in here to keep this bucket electrically neutral. So the positive ions flow from right to left. So if I'm looking at it here, they go from right to left this direction, or I could say towards the lead containing half of the wet cell. Number 6 says, which electrode is increasing in size? That would be the one that's gaining electrons, and therefore the positive ion right here is gaining some electrons and it's becoming Pb solid. And you can see this from the balanced equation. Look at what it's happening. The aqueous Pb, and I could put a little Aq down here since I know it's an ion, is gaining some electrons and it's becoming Pb 0 solid right here. And so the electrode that's increasing in size is the lead. Which electrode is decreasing in size? Well, that's obviously the manganese because it's the other one, but you'll see manganese is going from Mn to Mn plus 2. And so if you look at the balanced chemical equation, it goes from Mn to Mn plus 2, which is aqueous. And so the solid Mn is in effect disappearing and becoming Mn positive 2. Number 8, what is happening to the concentration of the ions in electrode A's solution? Well, electrode A over here, you can think of it in two different ways. If you're just talking about the lead ions, they're joining together with the electrons that are flowing in there and becoming Pb solids. And so the amount of lead ions is decreasing. But remember, the salt bridge is providing some new positive ions in there that are generally just soluble and aren't going to be affected. Could be like sodium or potassium or something that's a really soluble ion that's going to dump into here and not do anything or affect the flow of the electrons that's going in there at all. So you could say that there's no change because the salt bridge is providing some, or you could say that the Pb plus 2 ions are disappearing. Either answer is correct the way that this question is asked. Identify the anode, we did that already. The anox, that's the oxidized one, so that's the manganese. The cathode is the Pb because that's reduced. Red cat, remember red reduction is the cathode. The positive electrode, this is an interesting question. The positive electrode is the one that attracts the electrons. So that's right here. It's pulling the electrons towards it. And then the negative electrode is the one that's losing the electrons right here. So we have to say that Pb is the positive electrode and Mn is the negative electrode. 3 last questions. If electrode A were replaced with a She, what would be the EMF of the cell and the direction of electron flow? Well, first of all, what is a She? And SHE stands for a standard hydrogen electrode. And a standard hydrogen electrode looks like this. If you take a look at a picture in a textbook, a standard hydrogen electrode has a piece of platinum in it. And you can see that it's in 1 molar hydrogen solution. It has a piece of platinum wire in there. The reason they put platinum in there is because it's not going to react with anything. And then it has a 1 atmosphere concentration of hydrogen gas above it. This standard hydrogen electrode, if you look on the standard reduction potentials table right here, has a EMF or a voltage of 0. It's defined as what everything else is based off of. And you can see the half reaction for a standard hydrogen electrode is 2H plus 2 electrons makes H2 gas. And that's the reaction that happens inside of the standard hydrogen electrode when it undergoes reduction. Now, if it undergoes oxidation, it's obviously the backwards of that reaction. So we really need to replace electrode A with a She, a standard hydrogen electrode. So this guy right here now has become a She. And if you look at the standard reduction potential, which we just did, that has an electromotive force or voltage of 0. And then the manganese one remains the same, and the manganese was negative 1.18 volts. And so to find the EMF of the cell, the electromotive force or the reduction potential or the voltage, whatever words you want to use to say it, remember they all mean the same thing. You take the cathode minus the anode. And the cathode is the one with the larger reduction potential, and the anode is the one with the lower reduction potential. And you subtract those two. So 0 minus 1.18 gives me a voltage of 1.18 volts for when we replace electrode A with a She. And lastly, the direction of electron flow will be the same because it's going from the manganese to the She, because the She, the standard hydrogen electrode, has a higher reduction potential, and therefore it will be reduced, and the manganese will have a lower reduction potential, therefore it will be oxidized. So the flow of electrons remains the same. Practice one of these electrochemical cell quizzes on your own. See if you can get them right, and then come back and check your answers with each one of them. You usually don't get good at this stuff until you actually can very seamlessly flow between this language right here and be really familiar and not memorize, but be able to look up and use the standard reduction potentials in aqueous solutions.